Fear of God is the beginning of the wisdom. Lord, thank you for this day. Thank you for this one more opportunity to listen MATLAB lectures. Bless each one who are present in this meeting, especially the today's speaker, Mr. Anand. Bless his family. Bless all his friends who are coordinating to conduct this program. Bless also our faculty members who are attending this meeting and research scholars who are attending this meeting, and bless our management, Dr. Elizabeth Verghese, our Chancellor, Anand Jacob Verghese, Director, Ashok Verghese, for permitting us to attend this program. We ask this prayer through our Lord Jesus Christ. Amen. Anand sir, you can share the screen and start.
Okay, thank you, sir. Let me share my screen and yes, so I've started to share my screen and let me just put it in the other window. So if you have any questions, you can type it in the chat window. We will try to answer whenever possible. And today we have Janardhan as well as Shovik. So Shovik would be presenting most of the part today. So I would be starting off with the Z transform thing, which we left in the last discussion. And then we would be going to the other topics like differential calculus and ODEs. So there is a spelling mistake here, so that can be rectified. And following which we will discuss on PDEs, so which is the main topic of interest today. Partial differential equations, how it can be solved, and what are the different applications where it can be mapped to. And after this, we would like to give a brief introduction to Grader. And earlier we have sent out an email to collect the institute email IDs of all the faculties and research scholars. So based on that, we will show how we can enroll them as a learner and quickly show how they can answer to some specific problems that are assigned. And in the next week, probably next Friday on 30th, we will show the entire Grader workflow, both from the instructor as well as from the learner's perspective, how it can be used in giving out programming assignments in your respective courses. Following which, we will show you the different relevant courses, self-paced courses for this topic, which is how to teach using MATLAB. There is one self-paced course and feedback. Now, so we have 39 participants. So just to confirm again, so is my voice okay? It is clear? Am I audible? And is the screen visible?
Yes, sir. Yes, sir.
Okay. So this is today's agenda. So I was speaking about from this section itself. So this is in the form of live script if you see it. And we have made hyperlinks which could be done to link to the different parts of the program. So for example, if we go to Z transform, we have another hyperlink which will redirect us to the file name. So this can be done, and we will be using this framework in today's lecture. So the first problem is to solve a difference equation using Z transform. So in the last class we have seen what is the formula, mathematical expression of a Z transform, and how we can use functions to solve it. So today we will be focusing on a very interesting application which is known as rabbit growth problem, and how we can make the difference equation for this and solve it accordingly to predict the population of rabbit based on certain initial conditions. So this is a very well-known problem which says that suppose we have a pair of rabbits, and after every year they will mutate and we will have more rabbits. So every pair will mutate every year, and this is how the population will grow, right? So to represent this kind of thing, we can write a equation in the form of this. P of n plus 2 equals to P of n plus 1 plus Pn, where P is the population, current population, and n is the year, the current year. Okay. So if n equal n has to be greater than equal to 0, that is the assumption. It has to be a positive integer, so that if n is 0, so at the end of 0th year plus at the end of first year, so whatever is the population will be the population at the end of third year. Okay. So in this manner, the population will increase. So this is assumed. And if we want to use Z transform to solve this, then what kind of solution we would be getting at the end, and how we can visualize it or visualize the solution in terms of plot and actual numbers. Okay. So the first step is, again, you must have till now you know what this variable is. Sims variable is to define any symbolic variable as well as symbolic function. So here we are defining Pn, which will be a symbolic function, and Z symbolic variable. So if I run the first line, so you can see all the three variables appear on the workspace, where Z is the symbolic variable and P of n is a symbolic function. And of course, because we are using n, that it becomes another symbolic variable, right? And again, we are assuming certain things for the number of years. That is, it has to be an integer and it should be greater than equal to 0, and defining the equation and storing it in the in F. So let me just clear out the output for the time being, just to run the program from scratch. Yeah. So the equation, the difference equation is now defined, which was this. So we have represented it in the form of equation equals to 0. So F equals to P of n plus 2 minus P of n plus 1 minus Pn. All these are sent to the left hand side, and this becomes our symbolic function. Okay. Now if we want to apply Z transform to it, again we can use the library function Z trans, where we provide the arguments such as the function name and the instance n with respect to Z. So if you want to know more about this function, so there is always this documentation page. Let me just go there and show you. So you can go to the Z trans page and see what are the various ways you can use this function. Okay, either you can provide the function name, or you can provide 2 input parameters or 3 input parameters. So for the third case, since you are seeing there are 3 parameters, you can just go there and see what are the 3 different parameters. So suppose here we have symbolic variable n and z. Then we can provide the function. Here they are using another function, which is the Heaviside function, and they're providing these symbolic variables n and z to compute the Z transform. Okay. So from here, you can always revisit the documentation to understand what are the roles of different arguments, and you can compute it. So after running this section, I can see the equation in the form of this, where I still see this Z trans function is written here. Okay. So before solving this function, so suppose we want to solve this Z transform function, we cannot solve it. We need to simplify this Z trans term. Okay. So because the solve function that we use is only for solving symbolic variables. Okay, and Z trans is itself a function. It is not a symbolic variable. So for that, we need to substitute this term, Z trans term. So where we see there are 3 such terms in this expression. So for that, we have another function known as substitute. So we are substituting in this the earlier defined function fzt. And what are we substituting? We are substituting pzt, okay, which is defined here, into this particular term, Z transform of Pn, n, z. Okay. So when we substitute this, after that we can use the solve function to solve the Z transform with respect to this variable pzt. So let me run this section. So you see, if you see after the output after this second line, you can see all the Z trans terms have been substituted with pzt, and then we are using solve to solve this function with respect to pzt to get a simplified expression. Okay. So once we have this, the next thing to do is to do the inverse Z transform. Okay, we need to compute it to simplify the result and to get a solution. So we are just using this library function followed by a simplify function to simplify the expression. So let me just open both the things just to show both the expressions. So the first command that is iztrans is doing the inverse Z transform, and we get such a big expression where we have sigma 1 and sigma 2 as two other parameters which is defined in the expression. And when we use this simplify command, the same expression is simplified further, where we don't see that sigma 2 term now. So it has been removed after simplification, but we still have this sigma 1 term in this simplified form. So this is the solution of the difference equation that we had defined earlier. And now the question is, so in the last class, Professor, you mentioned, suppose we have a solution of a Fourier transform or a Z transform, then how to plot it? Such expressions are, it is mathematically large. Even after simplification, there are so many terms and so many constant parameters are involved here. Also, there is some complex term involved. Then how to visualize it in the form of plot? So for doing this, we need to do two things. One is to give the initial conditions which are required for the problem. So for this case, the initial conditions are in the form of P0 and P1, that is population at the end of the 0th year and the end of the first year. So which is 1 and 2, which we are providing as the initial condition. So suppose the population is 1, there is increase in rabbit population by 1 and 2 in the 0th and first year. Then what will be the solution? Okay, so we are just substituting again using the substitute command. We are substituting P0 and P1 with the values 1 and 2. So let's substitute it and see. So now it has substituted, and now it is further simplified. We don't have the sigma 1 term anymore because it was dependent on P0, P1, which is the initial condition 1 and 2. So half, if I put 1 and 2 here, half minus 2, so that will become some numeric value. It is gone, and we have this solution, but still we have this complex variable because it is a part of the Z in the mathematical formula itself. So once we have this solution, the next thing is to make the vectors. Okay, make the to come up with the values for the number of years as well as the number of population. So suppose we want to visualize it for 10 years, then we make a vector of size 10, 1 to 10. So let me just run this line and show you how the vector is created. So you can see a vector of size 10 where with an increment of 1, and using these values we are substituting into this solution, So if we run this will also be of a vector of size 10 with the values in it. However, we want to remove the imaginary part, so that is why we are doing a couple of more operations. First of all, we are converting it to double variable, and then using the real function, we are ignoring the imaginary part to get the final solution. Okay, and finally we are able to plot it. So here we are using this stem plot with the labels and grids. So I'm running this section. There is It's pretty, let's see. So now we can visualize the solution in the form of a plot too. Okay, where n is the vector that we created earlier, which is n values as mentioned in the x argument of the stem plot, and the y argument is the solution values, which is defined from this section. So replacing the n values into the solution and getting the vector of size 10. We're plotting x comma y, the simple plot command. But we can now see the rise in population, how the population is rising. Okay. So the interesting part here is that this rabbit problem corresponds to a very well-known term in mathematics or even in computer science programming, which is known as the Fibonacci series. Okay. So if you actually look into the values, so let me just show you p solution values. Yeah. So if you look into the values, you see at the end of first year, we have population growth of 2. At the end of second year, we have a population growth of 3. And this is a Fibonacci sequence. So you can add the previous 2 terms to get the next term. So 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13. So this is a well-known problem of rabbit population. You can search into Google also to know more about it, to represent the Fibonacci series, which is solved using a difference equation using Z transform. So this is about it. So do you have any questions or from this? You can ask or you can put in the chat window. So have you? So those of you are listening, have you heard of the term Fibonacci series? Means just to get an idea, you can just type a Y in the chat window. Then I would be able to know whether you are able to follow it or not. You can also type a no if you have not heard of the term Fibonacci series. So I see yes, yes. Okay, thank you. I see. Yeah, I see a lot of yeses coming up. Okay,
Anand,
yeah.
sir, they are those who are from mathematics and computer science. They will always enter yes only.
Okay, okay, yes. And I guess since we have around 49 participants, so the audience is mostly from that department. So, oh, I see one no also out of many yeses. Okay, so this is a very nice problem, interesting problem, which you can also probably include in your classes wherever you are teaching Fibonacci series. You can show these example to your students. Now the second part I will then pass over to Shovik. So for that I have to make him the presenter. So let me just stop sharing my screen once and let me see if I can make him the presenter. I'm
Sure,
passing the yeah, I've given you the presenter privilege.
Okay,
So,
thanks, Anand. And in the meantime, participants, if you can also put in the chat window your department. So we understand many of you are from mathematics. Apart from mathematics, if there are people from other departments, so we can also sort of message some of the things for your department if that helps. So if you can put in the maybe in the chat window like which department you are from, just write it down there and make sure that in the chat window you can say probably mention like everyone, so that everybody can see that, or all the panelists as well. Avionics, okay, great,
yes,
interesting.
because most of the chat that I am receiving, it is they are sending it to the host privately. So probably you can just select the to field to everyone so that everyone can see it.
Right, yeah, that will be helpful if you can make it to everyone in the chat window so that everybody can see it. Avionics, aeronautical, mechatronics, okay. So yeah, And I'm assuming there are people from mathematics as well. Great. Yeah, so aeronautical, we see that there are multiple faculties. Interesting. Computer applications. Okay, thank you so much. So we'll provide some of those information relevant, might be that will be useful for all these things. Physics, okay. Aeronautics, actually, since there are many of you, there are a lot of things in aeronautics we do in general. So if you want to have like discussions with us on that, on specific aeronautics later on, feel free to let us know. Okay, so I'll share the screen and I'll start from the same point where Anand left. So as you can see from where Anand was talking about, so he specifically mentioned about this live script, right? So we were using this live scripts. We are doing a lot of different things. So I'll use the same format. So we talked about the Z transform and how do we apply that to difference equation. So I'll go to the next part now. This will spend a little less time, and then the majority of the time, rest of it actually will be on PDAs. So on the differential calculus part, so I'll again go to this demonstration. This is just like while we are getting started, so when you have different type of functions, what can we do on those functions? And some of the things that come up in a very typical engineering mathematics course are like, how do we find out derivatives to a function? Also from first principle. So as you can see here, this is in live script, so we explain the entire concept. So if, for example, if for a function we want to find out how the slope is for that function, so if we have to do something like that, then how do we do that? Like the function that we define here is this one. So this is a cubic function, right? So fx equal to x cube plus 4x square plus x minus 5. So this is a cubic function which will have 3 real roots. And now if I have to find out a second line, which basically means if you want to find out a slope, then what we do from classic first principle, this is what we do. Our work in general for doing any form of this slope is fx naught plus delta x minus fx naught divided by delta x, right? So now how do we do that? You have already seen the symbolic function variable, so we say sims x, so that means x is a function of x is a symbolic variable. Then we define this function fx. So you have seen all these things, so these are more of like repetitions. We'll come to what we are getting into, but these are also things that will sort of revision of you have already seen. So if we have to define the function, we are writing here the function. So as we will write in pen and paper, exactly the same way we are writing the function. Then next, what we are doing, we are saying f plot. So f plot means we are plotting this function within the range of -5 to 2. So x we are changing to -5 to 2. So if I maybe see they get output on the right, so if I want output on the right, that's how it looks like. And then grid on is basically when we want the grid to be on. So I'll just run this and see what it comes up, and I'll come back to the stages what we were talking about. So now this is an interesting area. What is this line is what I'm going to talk about. So if there are 2 points, right? So x naught and x naught plus delta x. So the delta x part is this difference. So if the first point is -2.5 and the difference we are changing by this slider. So the difference between these 2 points, P and Q, that we are changing by this slider. So if the second point, so second point means x naught plus delta x. So if that second point is like at a distance of 0.9, so then what happens? So we are just plotting them here. So this is the function. And then once we have that, we are using hold on. So whenever you are using hold on in MATLAB, that means we are plotting on the same plot. So when we used f plot, so that means we are plotting this blue line. That is the function. And after that, what we are doing is we are plotting these 2 lines. So these two, so this is the first point. So this point is basically P, and this point is second point. So basically your P1, if you recall here, P1 is this one, right? So this is the first point, this is the second point. So we were just plotting the 2 points. Now, the interesting thing is, if you can see here, if the distance between these two is 0.9, then this is not really a tangent, right? This is a second line. This just intersects the curve. So if I want a derivative at this point, what do we need to make sure? We need to make sure this point is as close as P as possible. right? So that is why delta x has to be tending towards 0 in the limit theory. So what we can do is we can make this slider go all the way to the left, and then what happens, what we see here, we can see that this plot changes to this one where q goes very close to p, and then what we have is we create a tangent. So whenever we do anything in the form of differential calculus, this is critical, right? So this is a way to make it interactively for the students, when they can change this delta x value and see how they can make this tangent. So after that, what we are doing is very simple. We are just calculating the slope. So this is like the slope equation is this, right? M equal to fx naught plus delta x minus fx naught divided by delta x. That is what we were doing here. So we said fx, so this is fx naught, this is fx naught plus delta x, and this is the delta x, p1 minus p2. Those are the 2 points. So we calculate the slope here. And then all the rest of the things are all plots. And the label. So when we say x label, that means x. Title we can give like this and all those, right? Any questions? Does this make sense? Any confusion on this? Again, please feel free to put in the chat window. Just write it out and then we can see. So this is, I mean, just a differential calculus. I mean, we just end this. The rest of the things which is here is, if you have to do derivatives, I think this has also been covered. So in the derivative world, with if you think about any function, like this is the function, right? So if this is the function, this function is what? 3x minus 1. So if you have to find the derivative of this from first principle, then this is what we will do, right? Limit of gx plus delta x minus gx by delta x. So we are putting the function here. This is like mathematics. There is nothing MATLAB here. We are in the live script. We can put things in mathematical form. So we can use either the Microsoft equation or LaTeX equation, basically. So there you can see that equation and LaTeX equation. So if you do by first principle, the limit comes out to be 3. And in MATLAB, what we have is we have an inbuilt function called diff. Right. So here what we are doing is the same thing, symbolic of x. Then we are defining the function. The function is nothing but 3x minus 1. And then what we are doing is we are calculating the derivative of that. So if you have to find out the derivative, you can see that this is the function derivative 3. So like this, you can do any derivatives of any equation. You can do second order derivative, first order derivatives, and all those things. I think this has also been covered, right? But if you have not, if you have questions, let us know, and then we can cover that as well. Similarly, you can do integrations as well, like int is the command for doing integration. So you can do any form of integration and differentiation like this. So using this diff command, so you can do second order differentials, partial derivatives as well if there are two variables like that. So say for example, this one only, if I make sims x and maybe another variable I define as z, right? And then if I add this 3x plus maybe 5 times z square minus 1. So I'm just adding another variable. So now this g becomes a function of x and z, right? So now if this dgp, if I want to make this derivative with respect to say x, then I can say g with respect to x. Okay, so if I do that, then you can see what happens. So then you can see that this is the function 5z square plus 3x minus 1. If I want to take a derivative with respect to z, this is how it looks like. If I want to take a derivative with respect to z, sorry, this is a derivative with respect to x. So if I want to take a derivative with respect to z, then what happens is, if I run this again, so now you can see this is the derivative with respect to x. So then z is constant, so we get 3. And now if you want to take a derivative with respect to z, right, then what happens is this this becomes 5 times 2 times z, right? So 10z. So now 3 is constant. So you can take derivatives of different variables as well in this form. Okay. Any questions on this part? Is this clear what we did here? Is this understandable? Please feel free to put yes in the chat window if you can understand this. If no, feel free to put in any questions. Yes, clear. Okay. Thanks. Yeah, let's please use this chat window so that we understand, we can discuss with you. We don't want to make it like one-way communication. We want to make sure that everybody is communicating. And the chat window is a great area to do that. Okay, thank you so much for that information. Okay, so that's one. And of course, as previously, we will share all these things as well. Okay, now let's go to the ODEs part. The ODEs part has been covered again in the previous one by Suraj. So I'm not going to go into too much detail out on that. But yes, sir.
So it's
Yes.
you have shown the derivative, partial derivative, right?
Yep. Yes.
Yeah. Suppose the function is complicated function. So I want to find out the derivative at a particular point. What are the changes we need to make?
Okay, so first of all, if the derivative exists, like if it can be found out, then we can do it. If it's complicated, then it is fine. But as long as if the derivative exists, then we can find out using the same command like diff. But if the derivative does not exist at all, then we cannot do, of course. And the other part of the question that you mentioned, so we can find out the derivatives at particular points. So that's what we can do. If I just go back to the previous one. So what happens is, whenever we are finding out these derivatives, the derivative basically becomes a function. So this GPZ, this actually becomes a function of Z now. So what we can do is we can find out this function at specific points. So specific points means this instance now becomes a function of X and Z, right? So now say for example, if I have to find out this GP underscore Z at say for example X, and say for example if I say 1. Now if I just say this, I'll explain what I'm doing. Yeah, so so this function GP underscore Z, so GP underscore Z becomes a function of X and Z, and the variable, the function's value is 10Z. Now if I say X comma 1, that means I'm giving a value of X to this, like because it is a function of X and Z. So this contains the two arguments X and Z. Now if I said X comma 1, that means it is finding out the derivative at Z equal to 1. So if I give a value here 2, and then what will happen is it is finding out the derivative at Z equal to 2. So this is how, once we have found out the derivative, the general derivative, then we can give the input argument at the point we want, and then it will find out the derivative for us at that particular point. Okay, so that is the idea. And this function, it does not matter as long as it is a complicated function, it will do the derivatives. Just that we need to make sure that the derivative actually exists. If the derivative does not exist, like analytically, if the derivative cannot be found out, then it cannot give us. But otherwise, it will give the derivatives for any function. Does that answer your question, Simon, sir?
Yes, sir. Yes, sir. Thank you.
Okay, sure. Thank you. Okay. Yeah, thanks for that question. And like this, if you have anybody has any other questions, it will be great that if you just ask that. Okay. Now, I'll also, since many of you are also from, aeronautics or avionics and physics department, so we'll take up a little some of those examples which have some application front of you in these departments. But the underlying thing is the mathematics, of course, differential equation. So now this is a very simple one. This is a ball falling under gravity. So if you put a ball and then, I mean, of course, we can have complicated equations, but we are getting started with simpler equation. So when a ball falls under gravity, the weight is basically acting downwards, the drag is, which is the friction force, is acting upwards, and then this is the equation. dv dt is equal to minus g. So g means the acceleration due to gravity. So first of all, we'll ignore the drag part. Then it is this equation, right? Now how do we solve this? This is Sims. Now inside Sims, we are saying velocity as a function of time, right? So v as a function of time. Because this is time, this is a temporal function, this is a time dependent function, this is what we define. We are just defining g, which is the acceleration due to gravity, as 9.8. Now what is our equation? The equation is this. So if you compare with this, diff of v, that means diff is, now you know that diff means derivative. So derivative of v, by default, as you can see here, v is a function of t, right? V is a function of time. So when we say d for v, that means MATLAB will understand that this will be a derivative with respect to t, because v is a function of t. Now, if you recall here, what we are doing, this equation equal to, there is one equal to, right? So that is what is called assigning. And then here we are putting two equal to. So two equal to means this is part of the equation. So this entire thing is part of the equation, which is diff of v, this is dv dt, and minus g, right? So we just write the equation. So this is like a equation textual format. This is the actual equation in equation format. Now, once we have that, then we are setting the boundary condition. So if it's a first order differential equation, because now we are solving for velocity, right? So if you look here on the right, we also have the dv dt is this. Now, if it's a first order differential equation, how many boundary conditions do we need? We need one boundary condition, right? So that's what we are giving here. So what we are doing here, the condition, so we are just naming it condition, and then v at t equal to 0. That means at that very specific point when time equal to 0, that is also the initial condition, because it is a time dependent problem. So the velocity at time equal to 0, we are just given it to be 15. I mean, it depends. We can give anything. It doesn't matter, right? So we give the condition. So the condition becomes like this way. So we say condition equal to, and then again the double equal to is coming inside the equation. And then how we solve this? Desolve. Many of you have seen this in the previous one. Many of you probably has used this before as well. It's a very simple thing. Desolve. When we say desolve, this is the equation and this is the condition. So we say equation and condition, and that's about it. So we solve it. So when we solve it, this is the output we get. We get the analytical expression. This is the expression that we get. Okay. So now if you have to plot it, we use the command called fplot, the v, and then the range of time. So the range of time we are specifying at 0 to 10, then we are giving the x label and y label, right? So that's about it, what we have done here. Now, just taking this forward, here we are solving for v, right? But if we have to solve for position, then the equation becomes this, right? Because v is nothing but dy dt. So if you put v to be dy dt, then the equation becomes d2y dt square equal to minus g, because then it becomes a second order differential equation. But the concept remains exactly the same. The workflow, what we want to talk about, is exactly the same. So we define the symbolic variable. We say that v equal to now diff of y, right? So velocity is nothing but so we define the symbolic variable as y, velocity is nothing but dy dt, and the equation is nothing but dv dt. So either you can write this way, or the other option is you can also write diff of y as comma 2. That means it will be a second order y derivative. Okay, so this is the equation, right? dv dt is equal to minus g. Now this is a second order ODE. If you have a second order ODE, how many boundary conditions do you need? We need two boundary conditions. So that's why we are giving two boundary conditions now. So this is velocity at time equal to 0. This is y, the position vector at time equal to 0. So we are giving the specific values here. Okay, so we need to make sure that we are giving the specific values of this initial condition we are putting in here. Now what we need to do in MATLAB is we have to combine both the boundary condition in one matrix, right? So this is how we define condition 1 and condition 2, and then we say cond equal to in the, so you have already seen how to create matrices in MATLAB, right? So in a third bracket, when we put this space, so that means we are putting both the boundary conditions in one column, I mean one matrix. Okay, so once we do that, then we have the boundary conditions in this form. Then we can do the same thing. We use the same command desolve. We say equation and then condition, and then we solve this, right? Uh, so that's the solve comes out, and velocity becomes the derivative of it. So you can see now the distance becomes a parabolic motion. So this is the expression that comes up. If you look here, y as a function of t, and t there is a t squared term. So that means it's a parabolic curve, and that's why we see a parabolic curve here. Whereas v is a linear function of time, and that's why we have a linear graph. So we have the parabolic graph for position and the linear graph for velocity, right? That is what we expect. Uh, Now, taking this problem a little further, so there can be a situation, so whenever we are solving it analytically, that means we are solving a continuous system. There are times when we cannot solve an equation analytically for ODEs as well, right? And then what we can do is, because typically for this particular problem, this is called a hybrid dynamic system. Because in a hybrid dynamic system, what happens, if you can have both continuous dynamics as well as discrete transitions. Because typically, if you think about, when you drop a ball, and if you think about the damping effect from the wall and stuff, the ball will bounce back, right? And then it will fall again, and that sort of things will happen. So if we have to include those type of extensions to the problem, then the thing is, often what happens is we cannot solve it using dsolve, because we cannot solve it analytically. Then what we can do is we can use multiple numerical solvers, and inside MATLAB there are a lot of different inbuilt ODE solvers, numerical solvers, which is already existing. The ones that are already existing, it contains so one of them is a very common one, is called OD45. OD45 is a solver, which basically, I'll just mention what it is. I'll talk about, in fact, in a small second, in a second. So in that case, what we need to make sure is we discretize the time space. So here we are giving the time span from starting from 0 ending to 50, and the dt is the time interval. The time interval is we are changing by the slider. So for example, if I have a very high time interval, and then what we are giving the boundary conditions, like we have done it previously, we are saying 15 and 10. So those are the two boundary conditions. Then what we use is we use this command called OD45. Now, what is OD45? Let me actually go back to the MATLAB window. So if you write here edit OD45, you will find that this entire function comes out, which will give you the how OD45 works. But I'll just mention what it means. ODE means ordinary differential equation. 45 means it's a fourth order solver with fifth order error. So anybody who has heard of Rangekatta as a method of numerical method, this is a modified Rangekatta method, and this is already inbuilt. So the algorithm is already inbuilt, so we can use this function to solve it numerically. If you want to again see the solver, you can see here. So the source code of the solver is already existing. So like this, actually, there are multiple solvers inside MATLAB which are already existing. So this link actually is a nice one, which talks about which solver you want to use for solving any ordinary differential equation. And as has been mentioned to you earlier as well, this documentation in MATLAB is very strong. It contains a lot of different things. So this is like a book. It contains a lot of different things. So here it talks about how do we, what makes you choose a ODE solver. So if you have an ordinary differential equation, how do you actually make it, how which solver to use, and so on and so forth. So that is a critical thing which comes up. And the way we do this is we are writing the equation here. The way we have to write the equation is we have to write the equation in this format, where we break the second order ODE into two first order ODEs. Okay, so we define the equation here. So dx dt is a function of t and y. We say g equal to minus t2, and the function is this. So if you look into the function, then y1 prime is y2. So y2 is nothing but velocity. So y1 is dx dy dt, so which is the position derivative, that is y2, and y2 prime, that is what your velocity derivative is, that is minus g. And we write the two equations right hand side in this format. So for the first is y2 and the second is minus g. So when we write this equation, then MATLAB understands that it is solving this two first order differential equation. And the way we put it here is we say OD45. OD45 is the command, which is the solver. This equation num is the equation that we have created here. T-span is nothing but the time interval, and y0 is nothing but the boundary condition, right? The initial boundary condition. So now the next step is just plotting it. So the first step, why we do it numerically, is to see that this is, you can see this is very discretized. This is not a continuous one. So now if I change this dt to the other way around, let me run this again. So when I run this again and then change this dt to the other way around, then you can see it has become very smooth. So if the so we have discretized it, right? So if the time interval is pretty high, then we do not have a very smooth curve because it is discretized in time. But if I have a very small time interval, then again we can see that our time interval becomes smooth.
Shovik, we have one question from Professor Titus in the chat window. So
Yes.
let me just read it out. So he's asking that we say weight or drag is a vector with magnitude and direction. Can a vector be curved in shape instead of a straight line?
Yes, it is possible. Actually, that brings up another concept. So we can create vectors. I think what you are referring to is, say, for example, if we have vectors which contains directions, right? So in that way, what we can do is there are a lot of different ways by which we can draw vectors in the form with directions, basically. In general, for in different application plot, I mean, in the case of application, we call it like streamlines, or plotting the velocity vector, those sort of things. So what we can do is we can plot those things. So when we define the vector, that is basically a row or a column vector. But then what we can do is we can plot those plots as a directional concept. There is something called Quiver Plot in MATLAB. So I'll just show you the Quiver Plot thing. So Quiver Plot is a plot where we plot the velocity in the form of the direction inside MATLAB. Let me just quickly show you here the way this works. So this gives you the vectors in the form of these directions, and it can be curved, it doesn't matter. So the way this works is, let me just show you here. So Quiver, when we say Quiver, it requires the x columns as in the position. So every time this is the x direction and this is the y direction. So what we give here is the x coordinate, y coordinate, and the velocity in x direction, and the velocity in y direction. So basically, if you have four vectors, right? So the four vectors, I mean, if I put in more generalized terms, so we have the x and y coordinates, which are the position coordinates, and then the I mean, it can be velocity or it can be other vectors. I mean, it's just like these are vectors. So x, y are the position coordinates and u, v are the vectors in that direction. So then if we use this Quiver command, then what happens is we get a curved directional component of the vector as well. Will this be useful? Is this something that you are looking for that question? Okay, great.
Shovik sir, let us move on to PDE.
Yep, yeah. So we have done with these parts. So this is how you can do all these things. Yeah, we'll move on to the PDE part now. I mean, just before starting off with an example, I just wanted to mention on PDE, if you think about in PDE what happens, and you think about Matlab Logo, maybe you can put in the chat window while I keep on talking. If anybody knows what this logo means in Matlab, if anybody knows, please put in the chat window, and I'll keep on speaking. The way you can get the logo inside Matlab, because the reason I'm talking about is the logo is a solution of a PDE. The way this comes out is inside Matlab. Say, for example, if I say L equals to membrane 1, 100, and then if I say surf L, then you actually get the Matlab logo coming out here. So what this thing does this, yeah, this is a surface plot. So SURF is means a surface plot. And then the interesting part of this is the problem that is solved. This problem is a L-shaped membrane. So L-shaped membrane means this is a deformable membrane. So it's like, a handkerchief, which is a deformable membrane. But the interesting thing is, for that membrane, we need to solve the wave equation. And the wave equation is nothing but this: partial u partial t square, and then the Laplacian operator. So grad dot grad. So divergence of u, right? The Laplacian operator of u, this is equal to 0. So this is the wave equation. Now the thing with the wave equation is this can be solved analytically, but if we put a boundary condition in the form that this becomes a L-shaped membrane, such that if you think about a handkerchief, one quadrant cannot move, right? So then this becomes a L-shaped membrane because this quadrant cannot move. So if you put that boundary condition, then this becomes a problem which cannot be solved analytically. We need to use numerical techniques. Okay, and if you solve this using numerical techniques, then this gives you the Matlab logo. This became the Matlab logo because this was the PhD thesis of the person who wrote Matlab. His name is Professor Cleve Moeller. He's retired now. He's above 90, but he wrote the language in 1980s. But his PhD thesis, which was back in the 70s, was solving this problem. So the problem he solved in his PhD in the 1970s, he just wrote the MATLAB language to make this very easy in MATLAB, and then that became the MATLAB logo. That's just an interesting fun fact. If you want to know more, we have these links. Please feel free to go through them. So these links contains more. Now what we will do is we'll solve a partial differential equation for the wave equation. The problem here is physical problem. What we are discussing is a tsunami problem. The tsunami problem is, if I just explain this concept, because many of you are a lot of from different engineering domains. The problem here is this wave is moving, right? And this wave is moving, and then what happens in a tsunami is there is this high depth region, and then there is a shallow depth region, and near the shallow depth region the wave becomes very high. Okay, the wave height becomes very high. So again, as a live script, so I'm not reiterating the fact of live script. We have, I mean, we'll share this anyway, like all the time. So this contains a lot of details. Even if you, read through this, you will understand, because we have written all the things here. So I am not reading it. You can read it at your time. I'm just explaining it. So what we have here is this wave is moving. This wave is a function of x and time. So position and variable. The wave here, it's a deep water region. So the height is h2, and this is called the shallow water region. So the height here is h1, and when the water goes from the deep water region to the shallow water region, there is this transition region. So the transition region, this height is a function of x, because it is reducing from h2 to h1. Okay, and what we want to solve here is we want to solve for u, this u. So we want to predict the height of tsunami. Now, for solving this problem, let's go here step by step. I'll just explain this. This contains a lot of different things, so I'll go very slowly, step by step. Let me know if if things are clear at one point. So this is the wave equation, right? This equation we have put it in the LaTeX format. So the equation is nothing but partial u partial t square gh partial u partial x square, right? So this is a partial derivative of time and position. Now the way we solve it analytically is, first of all, we take this problem. So u is a function of x and time. So we take this problem from time domain to Fourier domain. Okay, so how do we do that? We take this transformation. So we convert our uxt as a function of capital U, which is function of x and omega, and then the time part e to the power I omega t. I means imaginary, the imaginary part of it. So this is what we want to do. We are converting the PDE, we are converting the variable u from time domain to Fourier domain. So that's why we are making this transformation, because what we want to do is we want to convert this PDE into ODE. For solving it analytically. This is how we can solve PDEs analytically in MATLAB. So once we do this transformation, so u become a function of x and omega and e to the power I omega 2. So then how does the equation look like? This is the equation that it becomes. Because this is just like this, right? So this is the equation that it becomes. So then it becomes, instead of small u, it becomes only capital U. So it becomes a ordinary differential equation. Now, something that we know is if you have a wave moving, then what happens is there are two waves passing, right? So in general, for you have like these two regions. When you have in the deep water region, you have one wave which is coming from this direction to this direction, which is coming towards left, and there is a reflected wave which is coming from left to right. I mean, the way these problems become complicated is because of this, because you have a wave which is moving from right to left, and then there is a wave moving from left to right. And the thing that it becomes is then the wave in general becomes a superposition of these two waves moving in opposite direction. Okay, so this is the standard solution, how it will look like, where you have two waves moving towards each other. Now let's go back. So this is theory. This is like in theory, you know. So now let's go back, like how do you proceed with solving this? So for the deep water region, in this format, this is how the solution will look like. So there will be a wave traveling to the left with a constant speed of root over gh2, right? So traveling to the left means towards the shore, say from the deep water region towards the shore. So this is one wave which is moving, and there is another wave which is coming in the reflected direction, where you have this amplitude r as a function of omega, and then e to the power I omega t minus x by c2. So this is in the deep water region. Okay, and in the shallow water region, you have only one wave because the reflected wave is not there. So in the shallow water region, we have only one wave, where this is, again, we have separated out, like it's kind of separation of variables, where we have separated because we have gone to the Fourier domain. So we have the amplitude as a function of omega, and then the time component is here. Okay, and in the transition regime, this is like this. In the transition regime, we have generalized. We don't know how it will look like. It's like generalized. So these are all the things which we need to know. Is this part clear, like the context of the problem? Any questions, please feel free to put in the chat window if you have. Okay, great. Now let's come back. How do we solve this problem? So then these are the variables, right? R is, if you recall, this is the reflected wave, T is the transmitted wave, and U is the amplitude of the wave in the transmitted region. So these are all the symbolic variables. So we are defining the symbolic variables. And then length is nothing but depth ratio times L. So these are the constant that we are defining. Now here is the important part. In MATLAB, we are defining the equations here, right? So how we are defining the equation? If you recall, we are saying the variables. So the variable is U as a function of T. So this is in the transition region, because in the transition region, the function looks like this. Capital U as of a function of X, exponential omega T, right? So this is our transition region. This is the one. So this is what we define here. Then U1 is in the shallow water region. Shallow water region means this region. This region, what we have here is T, right? T times exponential, then this. And then in the deep water region, we have this plus the reflected wave. So these are the three waves that we have here. Okay. So we have just put, like the way you will put in your paper, that the same way we have put in MATLAB. So like up to this was no MATLAB coding. This was writing. Here we have put in these forms in the form of MATLAB codings. So I'm just running this. Now we'll go step by step now for solving. How do we solve this? So first of all, first step, what we will do is, this is the wave PD, right? The wave PD we define here. So if you look all, what was the wave equation? So the wave equation was this. So partial U partial T square GH partial U partial X square. So that's what we are saying, the wave PD, and we are writing it the same thing. U. So as you were saying, we can take complex functions or not. So now this is a specific complex function. We are saying U as a function of T comma T. That means it's a second order differential, right? So this is the first term, which is nothing but partial U partial T square. The second term G times partial H. So that is the same. So if I go back, this is the thing. So H is also a function of X. So G times H partial X and partial U partial X. So that's what we are doing. Differential Hx and derivative of ux comma x. So this is the second order derivative. Okay. Now, if I have to calculate the slope at time equal to 0, like at a derivative at a fixed point, there was a question, right? Professor Simon asked like derivative at the fixed point. So what we are doing is we are finding out the wave PDE of generalized at t equal to 0, right? The initial point. So that's what we are doing it here. And then if we have to solve for capital U, which is the Fourier transform of small u, because small u was that x and t, we have taken that to the Fourier domain. So we have solving that using dsolve, right? And then we are saying slope ODs. So now let's see, once it has solved, this is the function that u has come up with. So u, it actually contains Bessel functions of jth and yth kind. So the second and third kind of Bessel function. And MATLAB automatically recognizes that the solution will be Bessel functions, and the Bessel functions come up here. So this is the solution that it comes up with. Okay. Now, there are two constants here that has come up, C1 and C2. So there are also the symbolic variables. We want to make sure that MATLAB will understand what is a constant and what is a symbolic variable, because the symbolic variables are constants which we can give values as well. So for doing that, we want to just create another variable where we want to have the constants. So then what we are doing is we are using a command called setDiff. Now what setDiff does, it creates a difference between two variables or something. Now here symvar, that means it will find out all the symbolic variables in u. So u contains so many symbolic variables. It contains C1, it contains L, W, X, A, G. So it contains all the symbolic variables. So what it will do is setDiff, will compare the u, right? It will compare u against these other symbolic variables. The other symbolic variables means depth ratio G, H, L, X, W. So if I do that, if I run this, then you see that it takes out C1 and C2, because C1 and C2 are the constants. So we are just extracting the constants. So say, for example, if there are other complicated, constants, then it will also give you the separate constants. So what we were doing is we are extracting the constants separately, because we want to solve them. We have to solve them, right? We don't know which the constants are. So we have to solve those constants. So we are just separating those constants out of this. Okay. Now, what do we have to solve? Now we have to solve, like if you think about it, the problem now, we have these two unknown variables, C1 and C2. And also we have these variables, T and R. T and R, we don't know. These are unknown variables. So what we have to do is we have to rely on boundary conditions now to solve for these four constants. So these four unknown variables, C1, C2, R, and T. So what can we do? The concept here is, so there, if you look into this problem now, the wave is coming from here, the wave is there. So imagine at this point. So what will happen at this point? This derivative u should have a continuous, so it should be continuous differentiable. So u at this point, right, at this point, when computed from the transition region and when computed from the deep water region should be equal, right? Similarly, u at this point, when calculated from the shallow water region and from the transition region, should be same. So the value of u at this point and the value of slope of u at this point should be same when we compute from the shallow water region. So basically, when we approach from this region and when we approach from this region, it has to be same at this point. So that is what we are doing at the next step. So we are here. So now you can see that this the function is pretty complicated, right? So we are calculating the derivative of u1 at against x, right? And then calculating the derivative. So we are calculating the derivatives of the u's. And then we create an equation such that capital U at L1 equals to small u1 L1 0. So capital U means from the transition region, because capital U is this, right? So capital U we have already solved for the transition region. So capital U at L1 and small u1, which is from the shallow water region at time equal to 0. So those two u's must match. Similarly, the two U's at the deep water region and the transition region should match, and same with their derivatives, right? So when we just do that, when we equate those, then what we can do is we can solve here. So the unknowns now, if you want to see the unknowns are C1, C2, R and T. So that's what we are solving for. So we are solving these equations. So solve. Now what we are doing is we are just using an equation command called solve, right? So solve, then equations, and then unknowns. So if we solve them, you will see that those are very complicated, right? So when you solve them, these are very big things that are coming up. So I can, you can make sure that you don't want to, if you don't want to see it, that is also fine. We can say that, clear output, so then you don't have to see it. But the fact is it can solve for those. So like this, you calculate all the constants. And then what we need to do is we substitute, because these are all complicated, right? We cannot substitute on our own. So that's why what we are using this command called subs. So that means it will substitute in the function that we have already calculated all these constant values. So once we do that, then we see that U becomes this Bessel function where sigma 1. So it contains a lot of different things. So this is what we have solved analytically. Of course, for since we are in the Fourier domain, we can also take limits and take omega to be 0. Because when we have to evaluate the solution, we can also make sure that if you want to see the solution when omega tends to 0, and then it becomes more simplified. So when we do that, use the simplify command, and we say this to be limit when omega tends to 0, then we see these are more simpler solutions that has come up. Okay. Okay. Any questions, confusion? Is this making sense? I went step by step. Of course, we'll share this with you. You can go through this as well, step by step. Is this clear? Any questions, confusions?
Savik sir,
Yes, sir.
can you show the last answer?
Oh, okay. So the last answer is this when we substitute.
Yeah. Ultimately, our aim is to find out the height of the wave in different place.
Right.
Right. And it depends on time, right? Whenever tsunami happens, the time parameter should be there.
Right.
I did not see any time parameter here. And
Yeah,
it is also depends on the depth. And the depth is unpredictable sometimes. In reality, the depth may change due to earthquake. The depth height, H1 and H2, maybe H1 may be same, but what about to H2? It may be affected by earthquake, right?
Right. Yeah, those are important points. So I agree. And then the thing is, once we go to that, I'll just open up. This is a simpler version which we have created for this. But of course, the next point comes when we go back to the time domain and then we plot it. Then we also see other interesting things. But what we wanted to show is like getting started with this. And once people get comfortable with this, then the next step comes out is when we want to plot this for different time intervals and for different variables. So I'll just show that as well since you asked. But if you want, we can share that file as well. That is also there in some extent in the documentation, in the MATLAB documentation for this problem. So basically, the way we need to do that is we have to make sure that we go back to the time domain, and then we plot it. We change all these variables, the variables that we need to give to. While I open up that, yeah, the variables, the length, so basically all the symbolic variables, we then need to make sure that we again change them to double so that we can give values to them, and those sort of things. So let me just open this thing. Yeah, so this is sort of the full-fledged one, which we are not talking about here. But the idea is once we do that, then how do we go back to the time domain and then actually plot it for different, different height variables and different time intervals. And then actually we see all these type of plots. But that includes another set of things that we need to do. So we sort of ended here. So after that, what we need to do is we need to give the values of these variables, because if we want to plot it and go back to the time domain again, so we have to give these values. So we give these values, and after that we give the solution, like the incoming amplitude becomes a function of time. So we give an input variables which is a function of time, and then we incorporate time there only, and then we basically plot it at different times when we have time as well. Just that we thought this will become a little more complicated at the first level, but if you are interested in people who are interested in further analyzing this, after you go through this first level one, then we can probably discuss with you on the next part of how do we plot the time, incorporate the time and plot the time as a function of time. Okay. But yeah, that definitely can be done, and that's the next step. But once you get comfortable with the ones that we have discussed so far, because also we are sort of the entire course we were starting up from scratch, and we are doing very step by step, and you have exams and all as well for this, so we didn't want to go into that level for this. But I guess for the people who are interested in further doing this, we can discuss with you separately.
We will, sure. We will.
Yep, does. Yeah, I think we are sort of running out of time. I just mentioned the last another example on PDE. So this PDE, this is actually a heat equation. This is also a Laplacian equation. Now, this is called the Poisson equation, if you know what Poisson equation is. So this is the Laplacian operator on U, and we are solving it on a unit disk, right? So a circle of radius 1, if you think about it. So the equation looks like this: partial U partial x square plus partial U partial y square equals to -1. The exact solution of this problem, if you solve on pen and paper, this is how it looks like: 1 minus x square minus y square divided by 4. Now, I mean, basically inside MATLAB, we have this partial differential equation toolbox, right? Now, the partial differential equation toolbox solves any PDE in the using finite element methods. It uses numerical methods, which is called finite element. But the thing is, we don't have to write finite element, or we don't have to write numerical methods or anything. It uses finite element method. But the idea is that's how any PDEs is solved using MATLAB partial differential equation toolbox. The way this is done is we say model equal to create PDE. These are all inbuilt functions in MATLAB. So we say create PDE, and that's about it. So if I just run this, maybe I can show you here. So I'll just clear everything first of all. Yeah, it's taking a bit of time. Okay. So if you run this part, so model equal to create PDE and geometry from this, I just wanted to show what this model is. So this model, this is something called an object in this programming language. So this contains a lot of different parameters. So it contains dependent coefficient, the coefficients, boundary condition, initial condition, geometry, and all this. So this is basically MATLAB automatically creates this. Now the geometry, we are saying this is a circle, right, out of this model. So this is how it looks like. How do we plot this? We say PDEG plot. So like when you do any plots in MATLAB, we use plot, right? So if you have to plot from this create PDE object, we say PDEG plot. So this is also an inbuilt command. So we say PDEG plot model and this. So when we do this, when we run this part, you will see that this plot comes up, and this is how it looks like. This is the circular disk that we have created. Now, if you have this problem, then what we are doing is we are applying a boundary condition. Again, these are all inbuilt commands. So we say apply boundary condition to the model, and the type of boundary condition we are applying here is called Dirichlet. So there are two types of boundary conditions, right? In general, the Dirichlet boundary condition and the Neumann boundary condition. So Dirichlet boundary condition is a fixed boundary condition. So that is what we are applying here. So it understands what a Dirichlet. So we can apply Dirichlet, we can apply mixed, and or any type of those. So we said Dirichlet, And for which edge, we say for 1:model is geometry dot number of edges. Now, what is this thing? Model dot geometry number of edges. If I want to see this, put it here. So you say model dot geometry dot number of edges is 4. So that means inside model, then we say geometry. So model geometry actually contains number of cells, number of faces, number of edges, number of vertices. So the number of edges here is 4. So 1, 2, 3, 4. Okay. Now comes the interesting part. So for the specifying the coefficients. So in general, what MATLAB does is, I'll just clear all the outputs. So what MATLAB does is, it takes any PDs of this form. So this form, if you recall, what is here, m times partial u partial t square plus d times partial u partial t minus gradient operator c gradient operator u plus au equal to f. Now, if you compare this equation with our equation, so I'll just bring up our equation maybe. I'll copy this and paste it here. So if you compare these two equations, so what is the value of m? The value of m is 0 because we don't have a time derivative here. If you have a time derivative, you can put that value, doesn't matter. Then we have d, right? So d becomes 0. So d becomes 0 because we do not have this term as well. Then we have this term. So gradient, so divergence operator. So gradient, divergence, gradient. So that is a Laplacian operator. So this is grad square, which is nothing but this partial u partial x square plus partial u partial y square, right? So c is 1. Now a, if you see a, we do not have. So a is 0 and f is 1. So specify coefficients is a MATLAB command. When we say specify coefficients, it specifies these coefficients inside that model. Okay, so once we have done that, the next step is generating the mesh. So because it's using finite element method, so we are generating the mesh. So we say H max. So H max is for the mesh. How much is the size we want? So we say model H max is H max. So that means this H max, this is the length between two nodes to be 0.1. And then when we use PD mesh, that means it will create this PD mesh. Okay. Next comes the results, where we use this command called solve PD. So we can just use this command called solve PD and put in model. So if we do that, then it will be solved, but it is already solved. So in your workspace, results has come up, and you can see results has x gradients, y gradients, z gradients, nodal solutions, and mesh. So nodal solution means at the nodes. So if I want to take the if you want to take the output is of u, right? So u. So u then becomes the results dot nodal solutions. And if I want to plot this, we use the command called pd plot of model, and then we say the xy data to be u. So if I run this, this is how it looks like, right? So model means it is again plotting that entire model, and then this is a syntax, right? If you go here, if you click on this help thing, the documentation will open, and then in the documentation you can see how it knows that. So whenever you say use PD plot, it has model, then XY data, and then this is how the syntax looks like. This is how you have to put in the command. So it knows what is XY data. So this is how you have to put it. Now, if I have to compare this with the exact solution, so as we have done it before, this is the exact solution, right? So what we are doing here is we are calculating the mesh nodes. So model.mesh.nodes, that means we are calculating the geometry, the position of the nodes. And then what we are doing at those nodes, we are calculating the exact solution. Okay, so at this point, we are calculating the exact solution at those nodes. And then we are plotting it again as the error. So u minus exact prime. That means the solution that we have got using this PD toolbox of MATLAB, and this is the exact solution. So we are subtracting that. Subtracting that means we are calculating the error. So if you want to plot only the exact solution, you can just remove this and then plot this. So then you get the exact solution. But this is not the error, the title. The error becomes when we say u minus this. So when we subtract that, then we get the error. So this is how the error looks like. So you see that there is, you can see the legend that these are, higher errors. Now what we can do is we might want to make it finer, like the mesh what we have is this. So if we want to make the mesh finer, let's check. So I can run this code as long as the error may probably gets to a certain extent. In this case, we make the mesh finer, and then we see that the error gets further reduced. So we can further reduce the error by refining the mesh, and that's what we were doing here. So this is one area by which you can solve PDs as well, and this actually goes to a lot of different examples. We talked about this. We can do this for a bunch of other problems. If I just show you, some of those which you can do. If you are doing, I mean, since there are people from different type of departments, if you are in physics, if you are in partial differential, I'll just open some of them. So say, for example, if you're solving like a dynamics problem. So this problem is of a tuning fork, right? In physics, you have this problem. So here, what you can also do is you can use import geometry if you have a geometry in some other file formats. So you can import those file formats. Like if you have something else, you can do structural problems. And like if you do this, the concept remains the same, first of all. So we, first of all, define the properties, then generate the mesh, and then use this command solve. So here we get these vibration modes and stuff. So you can do this thing. So once you get started, there are a lot of different things, and all these things also exist in inside the MATLAB documentation. So if you see here, if I go, if you maybe search partial differential equations. So the partial differential equation toolbox for MATLAB, this is how it solves. So if you go for partial differential equation toolbox, and then we go for examples. So you can see there is a heat transfer problem. So this problem actually, which we discussed right now, this is also a heat equation. So this is also a heat equation. So this is actually modeling how heat is propagating from the center towards the walls. Right. So like this in the examples also, you have a deflection analysis, heat transfer in block with cavity, electrostatic for physics people, Poisson equation is the one we discussed. So there are all these examples, but for all of them, the concept remains the same, like what we discussed right now. So this is what we discussed. Electrostatic potential, this is also the same thing. And this goes on for other examples. But all of them uses the same concept of solving the problem. Okay. Is this clear? Any questions? I think we're also running out of time. Okay. Anybody else has any thoughts? Thanks, Professor Titus, for your comments. Any other people? Any questions? Any thoughts? Is it understandable for your anything for your applications?
So, sir.
Yes, sir.
Maybe first time they were not able to understand the concept. Maybe they, while seeing the recording repeatedly, they can able to catch some point and they come up with the questions. My question is, how do we use the PDE solve to solve the linear homogeneous PDE? For example,
for analytically.
Yes, analytically. Like
that is
we
something
use
MATLAB cannot do. No? Yeah, that is something MATLAB cannot do, sir. PD solve is for in this method. It cannot solve analytically. No, it's just like MATLAB is not created for that.
So we can find out the solution for that. When we have a desolve function for single variable, why can't we can do it for two variables?
Yeah, so using so any PDs, if we break it up into multiple ODs, and then we can solve it. But this command solve PDE, this can only solve problems in this format. So this command, this called solve PD, if I just go to this,
maybe we can have a multiple sitting.
Yes,
so
sure.
Talk about this and find out a solution, because our ultimate aim is to find out a method, a MATLAB coding for solving homogeneous PDE with two variables. As you said, it is not available. Maybe we can sit and find out a solution. And coming to the tsunami function, tsunami problem,
Sure.
I would like to point out some points here. The as you said, no, the H1 and H2. That H1
Right.
maybe you can fix it. It won't be disturbed due to the uh, earthquake. But H2 is unpredictable, and the wave, how fast it moves, it depends on the another force. How do you calculate the speed of the wave? Any force acting on it?
Yeah, that depends on also how if we formulate the problem, right? The force. So you were saying
Yeah,
like what is the force by which this will impact on something?
yeah.
Yeah, so that probably
Now,
needs,
how
I
do
mean,
you predict the ultimately our aim is to find out the height of the tsunami wave in ground, maybe in H1, no? Uh, our aim is to find out the H1 wave. Based on that, we can give alert,
right,
right?
right, right.
And it is also depends on the speed of the wave, how fast it's moving, and what is the force acting on it. Many factors are there. Maybe we
Right,
can
right.
have a separate sitting and discuss. From my side, I can help you mathematical concept how we can use it. And
Mm,
from your side, if you can help us to find out the suitable MATLAB coding. And here we have a problem. We call it a string problem. Maybe that's why I told you I have sent a few copies for your reference.
right,
Maybe in the next meeting, you may please include that problem, string problem, where we talk about all wave functions. See this wave equation, there are analytical solution. We have 4 analytical solution, possible solution for a string problem. We have 4 solutions, out of which we select a suitable one, and that particular solution, if you can help us to find out MATLAB coding, so that will be helpful for our students to understand the wave, I mean the string problem. Not only string problem, the similar concept, similar method can be used for heat and one dimension heat and two dimension heat. Maybe in the next meeting, kindly please go through the material what I have sent. Based on that, we can take a problem and we can come out with the solution.
okay. Yeah, I mean, this problem we haven't, of course, included the force of the impact and all those things. This is
It
mostly for
depends.
the, yeah,
It must be. It depends. It is also. It must be included here. Then only we can talk about the speed, and based on the speed, the height of the wave, it also depends on that only. If the force is very low, it won't go up, right? Uh,
uh,
Maybe we can have,
yeah.
we can sit some more
Okay,
sittings
sure.
and we can come up with the solutions.
Okay.
And
Yeah, I think at this, yes, sir.
and for the Z transform, yeah, we learned a lot how we can solve through an application. You have said that's very interesting. If you can quote some other applications of this Z transform, it will be very helpful the next meeting. And here also in Tsunami Problem, we used Fourier domain. So usually we use Fourier series in solving a string problem. Please go through that also. Fourier
Mhm.
series, offering sine series we use to find out the coefficients. If you can
Mhm.
go through that part and come up with, maybe you can spend 10 or 15 minutes for this particular string and rod and plate problem. You can give a general program to understand the string problem, which is nothing but our wave equation. Is there any question from the audience? Mathematics department, faculty members, and research scholars, please feel free to post questions. Our team, Soik sir, is very helpful to us. Definitely, he will answer your questions. Soik sir, in the next meeting, we expect a solution for string problem, where like you can think of a guitar. The end point of the guitar strings are fixed, no? When you
Yeah, I mean,
play a
the thing is,
guitar,
sir, the point is like for this also we discussed, I don't know if Vice Chancellor sir is, because for this agenda, we have like a lot of different things, for the entire course. For specific problems, maybe we can discuss with you and the other faculties and
yeah.
go along with that.
Yeah, we can have a separate program for our student. In student program, we can include that. That's why I'm giving hint what we require, right?
Yeah,
For
we
that
have this
only I'm
assignment
giving it.
thing as well.
Yes.
So we will, I mean, since we are just also running out of time, I mean, there are, I guess Anand can also talk about that, because I mean, we have that assignment thing because uh, uh, we wanted everybody to complete an assignment for the next session as well. And that is
Anything you have posted in the chat box?
not
Yes,
yet, but Anand will go
not
through
yet.
that.
Yeah, so we will take some more time, maybe around 10 minutes. And also, Professor, I mean, since you are mentioning those problem areas related to string and others,
Yeah.
so if you are, means we will share these examples where you will find those syntaxes, you can refer to them again. And maybe if you can try from your side with your colleagues on those problems, and if you get some doubt or if you're stuck at some point, we can have a separate meeting with you in helping you out in that particular application, which is using either ODs or PDs. Then that can be done separately. And today we want to just discuss about that MATLAB grader platform, and which we will be covering in the next class on Friday 30th. So for that, so can I start now just to give a brief of how it will be done?
Yes, sir. Yes, sir.
Okay, then I have to again be the presenter. So Shobi, if you can just make me the presenter once again, I can just share my screen then. Okay, thank you. Let me just do that. I'm sharing my screen. Okay. Okay. And into the MATLAB window. Yeah. So the next portion that we wanted to cover is this. So we have already sent this register link earlier to you. So we have got more than 70 responses till now. So those of who you haven't filled it up, so for those I'm just pasting it again. You can just mention your institute mail ID. So that is the main thing we require, and we will just show you how we can enroll you. So today what we will be doing is that we will make you learners for a demo kind of course, and you will get access to some simple problem sets, and you have to solve it. So you will have more than 1 week of time. We will meet again next Friday or next week. So then we will show you the entire workflow. How what does it look like to be an instructor? What does it look like to be a student? And how we can use the framework for that assessment part. So for that we need your email ID, so you can fill it out if you haven't yet. And there are some getting started video and documentation also. So this we will share after the session. But now let me just show you the portion so that you can solve the problems, because now you will become the learner. And for that I'm showing you what will happen. So this is this Learn MATLAB course that we have created. This is a demo course. So I'm going inside it, and inside here I will be going to the manage people section. So right now I'm not showing how the assignment is created. It is already created. There are 2 assignments. The third one you can ignore. So it is, though it is created, you can ignore the third one. So the first 2 assignment has 15 problems. Okay, and I will be assigning going to this manage people section. So because I am the instructor, I can assign anyone as a co-instructor if there are multiple faculties teaching a same course, or I can assign as a learner to the students. So in this case, let me just copy paste the around 79 registrations we had earlier. So I'm just copying and pasting here with a semicolon after each, and trying to enroll all of you. Let's see it works or not. Okay, it worked, I guess. So now you see I've enrolled you all, and wherever I can see the name, I guess they have created the MathWorks account. In other cases, I guess this is because the MathWorks account is not yet created. So in that case, you have to just create your MathWorks account with your institute mail ID. That's it. and then you will be able to log into this grader platform in a similar way, right? And you will get a notification. You will get an email notification. If you follow it, you will be able to see this Learn MATLAB course, and you will inside the course you have to go through each of the problems. So how it will look like, let me just show you one page for the first problem. So this is the first problem where we are calculating a volume of a cone, a very simple problem. We know the radius, we know the height, and we have to store the volume in a variable small letters VOL, which will be compared for that automatic adjustment. So we need a reference solution for it. So I'm just showing you how it looks, how the reference solution looks like. So here we have defined R equals to 5, H equals to 12, and we are just writing the formula for volume, which is very straightforward, H into pi into R square by 3. And at your end, you will find this learner template. So you will find these lines will be blocked. You cannot change them, R and H. And you have to write the solution here. Okay, so you have to write this same thing. And if you write that, you will be able to, after writing that, you will be able to submit the solution. So that is about it. So I can also, since I'm instructor, I can also go to the learner preview just to show you how to do the first one. So I'm just I'm writing this thing, and suppose one thing to note, suppose I'm writing V instead of volume, the variable that was mentioned here, and I'm removing the semicolon. You can, before even submitting, so you will have you can submit each problem at least 5 times, so that is the maximum limit. But before submitting, you can always run the script to see the output either here, or you can write the same code in your MATLAB window just to verify before submitting. Just save the number of attempts to submit, but you will be able to submit more than once. Even I think it is right. So what I do is submit it. And I see that it is a wrong answer because I have not mentioned the volume. So that is why you need to read this question, and especially what is the variable name that is asked. So here it is mentioned you have to store in the variable name volume. So you have to use that because the reference solution will check with this variable. So now I'm submitting with the updated variable name. Correct. So that is it. So you have to go over each problem, and within it is all happening in your browser itself. You can just go to each problem and you can solve it. So for example, second problem is conversion of Fahrenheit temperature to Celsius. Formula is given. You have to just write. So easy set of problem just to make you comfortable. So that you become comfortable to this framework. And next week we would be showing you the entire workflow from the instructor perspective, so that in your upcoming semesters you can use this for automatic that assignment. So that is the main intention. Yeah, so this is one thing I wanted to cover, and also there's another self-paced course. So apart from the earlier self-paced course that was, I think, image and signal processing. So if you have done or if you have completed or started, that is good. But this is specifically teaching how to use MATLAB for teaching. So it is a 2-hour course. So we will share this script, but just those of you who are already there, I'm pasting the link again. So you can just go to this course and you can do simple modules. It will take around this amount of time. Especially the module 6 is dedicated to MATLAB Grader. So since you are MATLAB Grader, you can have a look at this also to understand the framework better. That is one thing. So yeah, that's about it for today, and we are again sharing the feedback form. So apart from that registration, if filled up, please do fill up. We will enroll you, and otherwise you can mail us. We can enroll you in case you missed out in filling that form. And I'm pasting the feedback form once again in the chat window for today. So you can mention your course names wherever you have ODs and PDs, what kind of application for all departments. So Simon has already asked multiple topics. So similarly, you can mention about your courses. We can see how we can help you along those lines. And earlier we had MATLAB drive. I hope you have access to it. So inside the same drive, we will add another folder day 6, and we will add all the demos that is covered today. So some of the demos might look complicated, as Professor Simon mentioned. So you can see the recording, you can refer to these demos, and you can see how you can apply it to your specific problems, how you can use those syntax and workflows. So that will be a very good thing if you can use it actually for your courses. So I do not have access to drive. Okay, oh, thank you for mentioning that. So MATLAB, okay.
I think
Let
that
me just show
that
you,
was a follow-up question. So yeah, I mean, there was a question, where can I find the live script for all the previous lecture sessions? So that way.
Okay. So let me just open the MATLAB drive and show you. Second, it is opening in the other window. Let it open. Okay, so this is the MATLAB drive, and here means, let me show you. So this is how the drive looks like, and inside this folder, so if I just create a link here, I will get this link. I can copy link here as well. So we will be mailing also, but since you are already present here, so to everyone, so you can access to this drive. I can open it in this incognito mode just to show you what it will look like. It will ask you to sign in with your MathWorks account, and okay, internet is slow here now.
So while this is loading up, since most of you will be enrolled for the grader problem, so basically you have to solve that problem. So all those problems that are there. So this is sort of an assess. These are all basic programming things, some things that we have already covered. So make sure you solve those problems, because we need to make sure that whatever we are covering, you all are getting exposed and trying out hands-on. Because other if it's not tried hands-on, nobody will remember all these things. It's something that we will all forget. This is only something that can be done through practice. So that's why this has been created. So this is a grader problem set that everybody needs to submit the solutions.
Yes, that is very truly said. Means, so that is the reason we have given very easy problems, means calculating a volume, so that you do it, and while doing it, actually those things you will be able to remember some of the concepts which you will require. Otherwise, after the lecture series, you won't remember unless you use it in some of your own problems. So this is, when you will open it, you have to just copy this folder. You have to go to add file, copy, click on copy folder. It will be copied inside your MathWorks and your account MATLAB drive. You will have 5 GB of storage. and then you can have access to all the days. So here we will add 2 days as well, and that is it. How you can access to MATLAB. So, so that's it. So next meeting next week on Friday to discuss on grader. Better on that. So up to that time, kindly complete that problem set. It has many of you can attempt. So it is not like you have to score high or so. Whatever doubts you have while solving it, you can list down those questions. We will be actually happy if we can discuss those questions during that session. So what are the doubts, your problems you are facing as a learner? Okay, you can show the instructor learner workflow, then it will be effective. And if you have not registered, register and drop a mail. So you can drop us a mail that you need access to that learn MATLAB problem set. We can enroll you as well, apart from the already enrolled ones. And please fill today's feedback form also. It will help us to understand better for the next session. So I hope every one of you have created the MathWorks account or know how to create a MathWorks account, because I think we have sent quite a few mails with respect to that, how you can create it. It is very easy. Just you have to use your institute mail ID to create an account. You will be able to create that. If you have access related issues, you can also.
Anand sir, we have uploaded
yes,
MATLAB MATLAB installer guide in our website. Program detail as well as the installer guide is uploaded in our website. Anyone who wants to know how to install, they can go through the website link. Even this FTP program link also, it is uploaded in the website. You can also check it. And this installation guide you can find it through quick link. That's an option. There's an option for quick link. If you click quick link, in which you will find MATLAB and Simlink. So if they click, they will get nearly 20 pages of PDF file where step-by-step instructions are given to how to install MATLAB software and how to create accounts. All the details are there.
Okay, thank you very much.
Thank you, sir. Thank you
for telling. You can also, if you can also share those links if for those who are not aware of that. Although it is your official website, so everyone must be aware of that. So thank you for mentioning.
Yes, sir. Yes, they can use it, sir. Thank you. Thank you, sir. Anand sir and Sovik sir for a nice presentation today, especially the tsunami problem that created interest to study that particular area where many faculty would not have known about this application of PDE. Is really helpful in real life situation. Thank you so much, MathWorks team.
Thank you, sir. Thank you, everybody, for joining.
Professor Simon.
Yes, sir. A participant, you can leave.
Thank you, everyone, for joining. So.
Yes, sir. Yes, sir. So to next week, we are going to concentrate on only on MATLAB grader, right?
Yes. So you have 1 week of time. So since I can understand academic session has started, so you will have a busy schedule. So based on your time, whenever you're comfortable, please go through that grader.
Yeah, Anand, we are losing you probably at certain times.
Yeah.
So on assignment 1 after that on Friday, then we'll be discussing on that grader workflow.
What about Tuesday? Coming Tuesday?
Coming Tuesday, there is no class. So this whole week we are, you can, we would expect you to go to that grader as well as the teaching with course, teaching with MATLAB on-ramp course. So that we have posted. That is a kind of post-session activity. So that will take some amount of time, 2 hours of time for that course. So if you can do some part of that, that would be helpful. Apart from that, the greater assignment. So that is why we are giving some
Yeah, we
time,
want.
and we will be
Yeah.
taking on Friday.
Yeah, since the participants are having this thing of solving the problem, they have this assignment. So that's why we don't have any class on Tuesday, so that they can utilize the time for solving these problems hands-on.
Okay, have you posted any link for solving, or we have to go through the grader?
It will come via
You
email. So
would be,
Anand just added
yeah.
everybody.
Okay. He will.
So an email will come.
Okay, sir. Okay,
So
so
just
much.
to
Thank you so
reiterate,
much.
yeah,
Mm,
yeah. Just to reiterate, means I've shared a link to register, means to provide the institute mail ID for that MATLAB grader assessment, and I've
Okay.
enrolled everybody who has filled that form till now. So anyone who wants to fill later can inform us. We will add them as well. Each of them will get a separate email through which they can just log into the browser, MATLAB grader, and
Okay.
they can get access to that course. So you would also be getting, in case your mail ID was present there, I just copied it in a whole manner. And
Okay,
do
sir.
let us
Suppose
inform in
so
case you,
while doing
yeah.
while answering your questions, if you get any doubt whether any team member from your side will be available on Tuesday during 3 to 5.
If you, yeah, we would like, if you get any doubt, please note it down, and we would be actually discussing those aspects on Friday. But even if there is some major doubt in terms of doing, you can drop us a mail. We will try to reply to you even before Friday. So whatever doubts or problems that you're facing as a learner, those will actually help us in the discussion during the actual session, so that it is we just don't show the framework, and you are not able to use it later. So that is why the plan is like that. So first give the assignment to you as a learner, then show you the instructor learner work.
Okay, sir. Thank you so much. Thank you, Anand.
Yeah, thank you, sir.
Thank
you,
you,
everyone.
sir.
Thank you, sir. Thanks,
Thank you.
everybody.
I would like to thank the management for giving the opportunity to conduct this event. Thank you. Thank you all.
Thank you. Bye-bye.
Bye, sir.
Thank you. Bye.
Bye.
Bye, sir. Bye.